Hello and welcome back to the lab. Again, thank you for everybody joining us here in the lab, and definitely thank you to all the patrons who help make the channel possible. You guys have wonderful suggestions, and your support, everything goes right back into the lab to make videos for YouTube. So thanks again for being there, and you are greatly assisting in bringing these videos to life. So thank you. With that, I've had a lot of questions both on Patreon and on YouTube itself if I do a deep dive into the attenuator section of a scope. So this is that video. I have a pile of parts on the bench, and the goal of this video is to help demystify the front end of a 400, 7,000, possibly 5,000. I haven't really looked into those attenuators yet, but essentially most of the front end of the scopes at a block diagram level function the same way. There are some nuances and unique differences between the two, but this is the deep dive into the attenuator section. This particular pile of parts is out of a 465B. It's one of the part scopes I got to help get my 465B up and running, because on mine, one of the attenuators was very far gone to the point where it was not salvageable. I had problems with the leaf switches up here that was causing just terminal issues with that attenuator. So I tried all the tricks in the book. Nothing worked. So I needed parts for that one. But with that, if you are interested in how the front end of an analog scope works, stick around. If not, there's not going to be much troubleshooting in this video. It's going to be mainly explanation and talking, but that's what I got for this one. So to get started on the attenuator, the BNC's the front end. We'll go signal. We'll do the signal path this way. So front to amplifier board. At the BNC, there's a ring here, which is the identification ring, which is insulated from ground, and that comes out on this pin right here. So this is not the signal. So right here is where the identification pin comes in from the ring. I've had one attenuator die here where this has gotten a leaky connection so that it was stuck in identify. It wouldn't come out of it. So that was actually a fault of the BNC itself, not the attenuator further back in the system. It was right up here. The insulation of the BNC went bad. This is the main input cap. This is one of the adjustments that we tune when we're doing a calibration. These are pretty fiddly. I haven't been adjusting these too much. This is actually way out. The way you adjust this is you crank it in, and as you crank it in is more capacitance, out is less capacitance. There's a Teflon sleeve, and then the actual connection of the capacitor is these gold wires that you can't see because they're behind this cap. This is a dead attenuator anyway. So there's the capacitive connection, ground over here. These don't really go bad. I've only of all the gear that I've tuned and all the videos that I've made, I've actually only had one of these go bad, these style capacitors, and it was in a meter, one of the DMM 502s. There wasn't quite enough. It drifted up. It drifted down in value. So the main input is right here. This resistor comes in to the main input. We're missing a part here. Let me grab one. So the AC and the DC path are a little different. So the DC path comes in on the resistor, hits the cap, which this is actually the outer shell of the capacitor. That comes down here for DC, hits the attenuator right here. AC goes through the capacitor to the other pin. That is selected by these two cam switches, and let's see, it sits in the scope this way. So AC position is both of the cam switches down. There's ground and there's DC. So AC, DC. All I'm doing to switch that position is this is the control that pokes through the front of the scope. That's the movement. And it moves this barrel this is a ground pin that's attached to the board when it's in place. There are also cam switches on the bottom of the circuit board. That's what makes servicing these kind of painful. Is to get the top ones aren't bad. The bottom ones can be a bear to get these out. To get these attenuators out, to really service these properly, you have to remove them from the scope. But to remove the attenuators, the vertical board has to come out. This has to be desoldered from the bottom board, which is actually this board right here. Here's one of the places where it's soldered in. There's bolts here, hiding under here, that bolt this to the front of the scope. There's a shaft that has to come out for the variable control, because this control right here controls the barrel switch on the attenuator, but the variable goes all the way through here, comes out the back with a nylon rod and attaches to a pot deeper on the vertical amplifier board. So getting these out is a process. Do it a couple times and you get pretty quick at it, but it's still probably 30-40 minute process to pull both out. So if you're gonna pull one out, pull the other one out. Do it too, because 3/4 of the work is done already. So the signal comes in, comes through the input resistor, comes through the capacitor, goes through the AC ground switches, and it hits our attenuator block. Now the attenuator block, these attenuators are different depending on what scope you're servicing. When I first opened one of the 465s up, that took me by surprise, because on a 7000 series you have a 10, a 10, a 5, and a 2. On a 465 you have a 100, a 10, a 4, and a 2. So not really sure how they get 5 out of those numbers, but this is the attenuator complement and it calibrated, so it's got to work. It's got to have something to do with these resistors that are coupling them together. All that's really going on here is each one of these attenuators is a different resistance value. And depending on what you have the front of the scope selected, you have a different total resistance switched in. At no attenuation, all the switches on the bottom of the board are closed, in which and signals coming in, diving down. Where it dives down is right here at these through holes. So that's one of the connections to the bottom side of the board. So depending on how it's switched, if you look, there's a switch. So if the 100x attenuator is switched in, the signal comes into the 100x attenuator, comes out of the 100x attenuator 100 times smaller, dives to the bottom of the board, comes over to the end of the board, and then hits the vertical amplifier section. If you have the 100x and the 4x switched in, it essentially does up and down, up and down, up and down as it's going through the attenuators. So it comes in, goes through the 100x attenuator, goes below the 10x, bypasses, comes back up, goes through the 4x attenuator, comes down, bypasses the 2x attenuator, and comes back up and out the back. This is the final point where it leaves the board and goes into I believe it's a FET. I think it's a JFET. Is the first amplification stage before it hits the vertical section of the scope. Wideband amplifiers are incredibly difficult to make, especially when you're talking about 100 megahertz, 200 megahertz, 300 megahertz, 350 megahertz. I actually have a 485 attenuator block that I'm going to bring out towards the end. And I have some 485 scopes that we're going to go through as well. Have two of them. One's got some pretty neat options on it, and one is eye-searingly blue. Making a wideband amplifier is very difficult. So what they did was they made a fixed gain amplifier, because you can make a wide bandwidth fixed gain amplifier, or I should say making a wide bandwidth variable gain amplifier is incredibly difficult. So they fix the gain of the vertical section of the scope, and then what they do is through the attenuators they cut the input signal by a known calibrated amount. So if I have a 500 volt signal coming in, for the sake of argument, it makes the math easy, and I have the 100x attenuator switched in, I get 5x, or I get 5 volts over here. So 100x comes in, 10x attenuator, 5 volts here. We get an additional 10x attenuation on the front end of the scope from the probe. We can get an even additional 100x attenuation or 1000x attenuation depending on what probe we hook up to the front of this. Now, for a 465, they can't compensate for a 100x or a 1000x probe. A 7000 series scope actually has 100x and 1000x probes that go with it, and they can understand. They'll adjust the readout accordingly. The readout on a 465 only goes up to a 10x. You can still use the probe, you just have to do the math yourself because the scope can't do it for you. Technically, it's not doing any math at all. All it's doing is switching an LED to show you what your volts per division is. And it does that from the sensoring here. So the amplifier on the scope, which I don't have at the moment, because this is the channel select board. This is the channel select board. This is not the vertical amplifier board. You can see plenty of that board in the previous video where we did the vertical section in a 465. So we get a calibrated voltage at this end of the attenuator into that JFET that allows us to get the bandwidth out of the amplifier without running into the variable slow bandwidth, because scopes need to be pretty quick. Now, some 400 series scopes like the 485, they have an additional section which makes them even more complicated because they have 50 ohm input. This is just a 1 meg ohm input. There's your 1 meg ohm input right there. That's just a 1 meg ohm resistor. The scope probe sets up a voltage divider between the resistor and the DC, the BNC jack, which is how you get the additional 10x attenuation. A 10x probe is not a 10 times amplifier. It is a 10 times reduction in signal coming into the front of the scope. So we can put more power in it without blowing up these attenuators. Because what really burns out if you overrange a scope is these attenuators tend to go first because of their impedance matching and things like that. I believe these are carbon resistors. I've taken a couple of these apart because I've had to clean them. But they are easily damaged by overvoltage and driving them too hard. So these will burn out before the vertical board will, because those are more fragile. That is a big problem with these 7A19 and 7A29 plugins. These are 50 ohm inputs, and for whatever reason, a lot of people go, I can hook a transmitter up to this. I want to see what the transmitter's doing. And they dump 1,000 watts into this out of a power amplifier, and it's only rated for 2. So they pop the inputs on these. There's a lot of these with burned out, damaged inputs. Still have the same attenuator section, same style, same switches, same everything. Just lower impedance because it's a faster plug-in. This is a 500 megahertz plug-in. This is a 100 megahertz attenuator. And see, this one's even different. 10x, 5x, and 2.5. This actually, now that I look at it, even has some more limited voltage ranges. This doesn't get the up to 5 volts. So this is missing a 2 volt and a 5 volt off of like the 465 has. Still, very useful plugin. The barrel switch on the bottom is what is cammed to make the right switches go up and down as you turn the barrel switch. So you can see the different cams coming in as the barrel switch rotates. As they go down, they ride on the tiny plastic, the top of the cam switch. And what happens is it pushes that down. So like this switch is down, this switch is up. They don't move very far. As the switch on the bottom comes up, it pushes a pin which pushes the switch on top up. As the switch on the bottom is released, the switch on top pushes the switch on the bottom back down and away from the board. We'll pop this out. This is our special. Now these caps, I've never had one of these go bad, but these are actual Tektronix capacitors, and they're funny because of the DC path. This side to the case, this is the DC path. Pin to case to pin out to the board. The AC path is through the capacitor to the pin. So there's this extra pin just soldered onto the case of the capacitor, and it's just sitting there. So never really had one of these go bad, but it would be interesting to have to duplicate that if I needed to find one. I don't even know where I'd find one of these. But so we have solid steel case. There's the insulating material, but that's a DC path. Pop these standoffs off. If you ever have to take the barrel switch off of one of these, the standoffs are there. There's 2 other standoffs here, and then there's 2 screws here. All 6 have to come out. One word of caution when you take the barrel switches out, there is grounding pins here. These will like to fall out because the screw actually holds those in place, and that actually has the screw threads for that hole. So make sure you just notice where they are, and in case one falls out, because they do have a tendency to kind of fall apart. This is going to come apart. Usually I don't take them apart like this, but this is a dead attenuator. So the construction of the barrel switches, this inner plastic ring is very fragile, especially with the age. It gets brittle, so if you put too much torque on a connection, it'll pop that this inner cam, and it'll wreck the barrel switch. I have a 465 that is dead at the moment because this this barrel cam got split off and cracked before I got it, so the knob just free spins. But be careful how much torque you're putting on the barrels, because that is a fragile part. On some of the scopes that I've run across and I've serviced, there's been a dry lithium grease, I'm guessing, that's been in this cam. This one doesn't have any, but it's like one of the, it's that white lithium grease. I'm not sure what you would use to lubricate this section. You don't want to lubricate this because you don't want grease getting on the finger switches. But just this area, a little bit of plastic safe, if I can find some plastic safe lube, just to extend the life of the cam, I'd put a little bit in here. Don't really have a good solution for that yet, but just on this, not out here, just a touch, not a lot. Here is the bottom side of a cam switch. So as you can see, there's a straight through path. I don't know why they did this, but every scope I've taken apart has this on there. To really clean these cam switches right here, you have to desolder this shield and pull this off. I don't know. This is the bottom of the DC AC ground switch. Here starts the attenuator. So there's the delineations between the two. Come to think about it, I've never had to separate. I guess the board is easier to clean. If you pull these two screws off right here, this one and this one, you'll separate the metal frame from the board. This is not a traditional FR4 circuit board. This is like a ceramic, or I think an alumina ceramic or some material, not normal PCB. You have to be very careful with what cleaners and things you use on here. The Tektronix prescribed cleaning method is isopropyl alcohol only. Put a piece of paper in there, close the switch on the piece of paper, and pull it out. And you just keep doing that. So paper in, soaked in alcohol, close the switch, pull it out. And then you just keep doing that until the contact is clean. That is a method that I use to service these cam switches. I have run into some scopes that are stored very poorly. The last 465 that I did was one of those, where that is not enough. This is a gold circuit board. However, gold does get kind of cruddy. So I did use red deoxit on the cam switches. Very, very small amount. I took a little bit of flack from that. I'm doing a test on that 465 that to see if that actually works or not, or if it is going to damage the attenuator. I don't know if it's going to damage the attenuator or not. Red deoxit's supposed to be safe for use on all surfaces, things like that. Did not peel the PCB off. I checked the scope before I sat down to record this video. The attenuators still work perfectly. I would consider that a short-term test. I'm still doing the validation. I'm not ready to say that that's a good method of cleaning one that the alcohol method doesn't work on, but the alcohol method didn't work on it, so I was at the point where I had to try something. If the alcohol and paper method works, do it that way. It's the safest way to do it. Absolutely. Getting to the bottom ones is kind of a pain in the butt. You got to take it out about this far. So a complete disassembly, if I pop the, see if I can, I will try to do this on camera. Here's one. Two. Gentle prying up. And then I use a, if I can't flip the board over like that, I use a pair of tweezers and I just pick them out. So, let's finish pulling the board apart. Now I'm going to save this attenuator board because this one actually still works. I've had it this far apart before, so yes, I will be able to get it back together. Don't bend the switch. Bending the, over-adjusting these finger switches is terminal on these boards. You have to be super careful when you're adjusting these finger switches. There's not a lot of room for error, and there is not a lot of room to fix it if anything does happen. So, but this is it. I mean, this is what this plus, let's see, its front is this way. It's 110, 4, and 2. So that is an attenuator outside of, I should say a complete attenuator outside of the scope. Because the barrel's off and all the reed switches in the bottom are down or are up, it would be at its highest attenuation value. So the 100x, the 10x, the 4x, and the 2X are all switched in. That being said, let's see what the DC resistance is of that path with it all switched in. Neat thing about these attenuators, they're 100% passive. They work even out of the scope. I have the board supported on the rails just for so I don't close the switches on the bottom side. So signal comes in, we're here. We'll measure at this point right here and this point right here. And with all the attenuators switched in, we are adding 1.3 megohms of DC resistance. So as it's going in, out, in, out, in, out, in, out, we're adding, all total, this would be 50 volts per division at its highest setting. Probe would be 10x, so that's 9 megohms. The input's a megohm, so we're at 10 megohms, plus an additional 3 megohms before it even hits the amplifier. So the 50 volt per division signal at the probe tip, we've attenuated by, it's 10 megohms at the front of the scope, 11.3 megohms before we hit the vertical amplifier. So what I'm going to do is I'll move up to the 6510. I'll get the 4-wire measurement out, and we'll do 4-wire measurements on all the attenuators, and we'll just check and see what their resistance is. Okay, I've got Kelvin clips, and we're all set for 4-wire measurement. This is the 2X attenuator. So what the signal path on these is through the center 2 pins. So that's what I have to measure through. So the signal goes in, through, and then back out on the center pin. So it makes a U through the attenuator. So I set it to 10 power line cycles, manual trigger, gives the best accuracy possible. So 500K, 0.500 meg. Keep in mind, this is also the DC resistance. There's a lot of AC components that we're not even looking at. This is the 4X. The 4X is 750K. This is the 10X. Just shy of 1 meg, 900K. This is the 100X. Almost 1 meg. So right at about a meg, 1 meg. I can't do any capacitance or inductance testing on them. I don't have an LCR meter yet, but it's on the list. Just don't have one. Okay, here is a 350 megahertz attenuator. So this is the attenuator block out of a 485. I do have a couple 485s that I haven't shown on the channel yet, but they are on the way. Definitely read the manual. This board material is no joke. It's easy to break. So we're at High Frequency City here. Here are 2 attenuators. There's a 100X and a 10. Cam switches right there. Power and AC, DC, and ground is there. I haven't done much with the 200 megahertz scopes yet. One of the main differences with the 485s and the 350 megahertz is it has a 1 megohm, 50 ohm switchable terminal on the front of the scope. That's one of the reasons why this module is much more complex. This is actually one of the amplifier ICs, custom tech part. So it's got a switchable input. There's a lot more to the calibration on these. It will be a long video. Let me pop the bottom of this off. See if I can at least pull the shield off so we can take a look at the bottom. But from a serviceability standpoint, The 485 modules come out a lot faster than the 465. This is the potentiometer for the variable adjustment that I was talking about on the further back in the scope. In this one, it's attached to the module. Here we go. Oh, those grounding fins sound terrible. I feel like I'm breaking something, but I'm not. There we go. There we go. Some of the micro coax that Penulta coax that Tech is known for and uses everywhere. So on this one, if I remember correctly, yeah, it is. I do remember correctly. The bottom board on this one is the 50 ohm board. So this is the 50 ohm attenuator. This is the 100 meg attenuator. So if I remember the spec sheet correctly, 200 megahertz on this one. 350 megahertz at 50 ohms. So even the 485 can't hit 350 megahertz at 1 mega ohm. It just couldn't do it. But it does it at 50. Now on this one, we have actual resistors. They're not even tunable, so they're just there. This is, I believe, if I remember correctly, this is a fuse. Pretty sure that's a fuse. So there's a lot going on in this module. So this is the attenuator from a 485, but they come out real quick, so they're not awful to work on. Also, stuff like this, where leads are in the air, they're just kind of flying, things like that. They're supposed to be that way. They're done that way on purpose. This transistor looks like it's bodged in. It's not. It's supposed to be that way. And everything looks kind of like it's crowded and on top of each other. It's to keep lead length short because it's a high frequency board. Like here, there's even a capacitor piggybacking on a resistor. Also, when I said those attenuators in the 465 videos had been stored poorly and I needed to use some contact cleaner on them. This is the channel switching board out of that same parts unit, and I just want to show you guys, just want to show everyone. I don't know how this was stored, but these pins are black with corrosion. Like, it is horrible. I haven't seen pins that bad in a while. To give you an idea, that's what the inside of the socket looks like. So the attenuators in that other scope were in pretty bad shape. So this is also, I've talked about these in a couple of other videos. These are those really crappy Texas Instrument sockets that if they're giving you a connection problem, they need to go. Some of them still work, some of them don't. But if you suspect the socket's a problem, it may be a pain in the butt to get rid of it, but it's got to go. Thanks for stopping by the lab today, taking a look at a deeper dive into the front end of an oscilloscope and the Tektronix attenuators. I do hope this video answered more questions than it created, but if it did create a bunch of questions, I will see everybody in the comments as usual. With that, I will see everybody in the next video.